Well, good morning, everybody, or good afternoon, wherever you may be. And we've been talking about equilibrium, right? And today we want to get into this idea a little further about my equilibrium constant. And if you recall from last time, first of all, we said, hey, equilibrium is when I have a reversible reaction and my forward rate, right? The forward rate of my reaction equals my reverse rate. And what's important to remember here is that this does not mean that my concentrations of my products and my reactants are equal. It doesn't mean that my partial pressures are equal. What it means is they are not changing. It also does not mean that the reaction has stopped. The reaction has continued, but it's just that, like we say, the reaction forward rate, the rate of the forward reaction equals the rate of the reverse. And we said anytime we have something at equilibrium, we have a constant, and this constant is called the equilibrium constant, the KEQ. Now, what I didn't maybe get into quite as much is that this is a generic term. KEQ kind of is an overall generic term for a whole bunch of Ks. We can have something that is a Kw, the equilibrium constant of water. We can have a Ka, which is the equilibrium constant for an acid. We can have a Kb, which is the equilibrium constant for a base. We can have a Ksp, which is the equilibrium constant for a saturated solution. And the two that we want to focus on now are the Kc and the Kp. Well, really, we're going to focus just on the Kc, but the Kp is similar to the Kc. The Kp is really aimed at gases, and what it is that your equilibrium constant is written in terms of partial pressures. All right. And so only gases matter and only partial pressures matter. And so when you were to write a Kp, it would be something like, the partial pressure of O divided by the partial pressure of N2, right? And maybe those are squared or something, right? Who knows? But that's the general form of Kp. Kc is the one we're going to focus on now. And this is for solutions and gas mixtures, all right? Either or. But this is my equilibrium constant in terms, written in terms of concentrations, right? And so just to recall on this, right? When we're doing this, if I have A to the A aqueous and B to the B aqueous, going to C to the C aqueous plus D to the D aqueous, then my Kc is the concentration of my C raised to the C power, the concentration of D raised to the D power, over the concentration of A to the A power and B to the B power, right? So that's the form. And notice, these are all concentrations. We do not put pressures in here. We do not put anything that's solid in here. And we do not put liquids in here, right? Now, gases have a concentration, so I can write my gases in this form, all right? And this has to do, really, this is with mixtures. Good. So that's kind of the background. And today we want to get into some calculation. There's two calculations that we want to talk about. The first one is, oh, and by the way, I should point out here, what? That these are not just normal concentrations. These are the concentrations at equilibrium. These are not initial, but these are what we would call equilibrium concentrations. All right? Good. So the first type of question, so we'll call, type 1, what you want to do is you want to calculate or determine, you want to calculate Kc. That's a Kc. Ooh, nice. Yoink. That's a Kc. and you're going to be given your equilibrium concentrations for both products and reactants. All right? The second type of problem we want to do, and we'll call it a type 2, is that you're going to calculate a equilibrium concentration for one of the products or reactants, and you're going to be given the Kc and all remaining equilibrium concentrations, okay? So those are the two ways to do it. So let's take a look here. Let's take a look at a possible problem, right? Okay, here we go. I've got nitrogen reacting with hydrogen to form ammonia. They're all gases. It is at 300 Celsius. Given the following equilibrium concentrations, what is the Kc? So we want to calculate a Kc, and they give us equilibrium concentrations for each of our reactants and products, right? Good, so what's the process? Number one, first thing you should do, zoink. Number one, write the expression for your Kc, right? So you're going to write it in terms of your concentrations. Two, input your equilibrium concentrations into your Kc expression. And then number three, solve. That's a piece of cake. Solve for your Kc, right? Good, so here we go. Are you ready? Number one, what did we say? We want to write our Kc equation. So Kc is equal to, we're going to take our products, concentration at equilibrium and raise it to the power. My product is ammonia, so I'm going to take the concentration of my ammonia at equilibrium. Just to remind myself, I'm going to put a little E down there. And then put a 2 up here. And then what am I going to divide it by? The concentrations of my products. And remember, they have to be gases or aqueous. These are all gases. So this would be N2, equilibrium raised to 1, and H2 at equilibrium raised to 3. So there we go. I have my formula, my expression. Now I'm going to input this data in here. So my Kc is equal to, what's ammonia? Ammonia is 0.715, and I'm going to square that. Divide that by my nitrogen. Nitrogen is 0.647 molar times my hydrogen, 0.435. And what am I going to do with the hydrogen? I'm going to cube it. All right, so now let's get out our handy-dandy calculators. Link. 0.715. I'm going to square that. I'm going to divide it by 0.647, and I'm going to divide it again by 0.35 cubed, 0.435. And, oh, no, that doesn't look right. Let me go up. I must have made a mistake. Oh my gosh, horrible. Let's try that again. Clear. So let's try that again. 0.715 squared, got it? Divided by 0.647, divided by 0.435 cubed. And I get 9.599, 9.60. Woohoo! Perfect. All right, that's how easy it is. Good. So if you know how to use your calculator, like apparently I don't, you should be able to do this on this question. Pause me and bring me back when you're ready. All right, piece of cake, right, ladies and gentlemen? Kc, write the expression. What is it going to be? First of all, notice none of these are solids or liquids, so they're all going to be in my Kc expression. I'm going to take the concentration of my HI, and it's got a coefficient of 2, so I'm going to square that. Just to remind myself, I put a little e to say, oh yeah, that I have to use an equilibrium concentration. And then I'm going to divide that by the concentration of my I2 at equilibrium, and I'm going to divide that by my concentration of H2 at equilibrium. And now I'm going to put these numbers in. What's HI? It is 0.202 squared divided by, what's my I2? 0.0172. Yeah. And what is my H2? 0.0433. Yes? Okay, let's put this in. 0.202 squared divided by 0.0172 divided by 0.0433. And I get a number that is 54.8. 54.8. All right, not bad, ladies and gentlemen, correct? Easy, easy. All right, so now let's move on to our next kind of question. And what we're asking for here is we want to know an equilibrium concentration, right? Given the following concentrations, what do I want to know? I want to know my equilibrium concentration of NH3. And what am I given? I'm given a Kc, and I'm given the other equilibrium concentrations. Good. So what's the first thing I want to do? Write my expression for Kc. My Kc is equal to what? All right, notice these are gases, so they would be in my Kc. They're not liquids or solids. So what do? So I start with my ammonia, sorry about that, square it. I'm going to use an equilibrium concentration, right? And I'm going to divide that by the concentration of my nitrogen at equilibrium times the concentration of my hydrogen at equilibrium, and that hydrogen at equilibrium is cubed. All right? So we have this value, right? And we have these two values, and we want to find that value. So you may have to do a little algebra here, right? And so what I need to do is multiply both sides by my N2 and H2 so that I can get my NH3 by itself, right? So what I'd get, let's do this to both sides. Concentration of N2, concentration of H2 cubed. Do that to both sides, right? And I'm going to do the same thing over here. And what do I get? So then I get Kc, concentration of N2, concentration of H2 cubed, and these guys then would cancel, and that equals the concentration of NH3 squared. Now what do I have to do? Well, you have to take the square root of both sides, right? Don't worry about that. Sorry about that. So what do? I take the square root of both sides, and I get then the concentration of NH3 is equal to the square root of Kc times my concentration of N2 times my concentration of H2 cubed, right? Now, those are all equilibrium, and now we can put in some values. So this would be equal to square root. What's my Kc? 9.60. What's my concentration of N2? 0.226. And what's the concentration of H2? 0.895 cubed. All right, so let's get out our calculator. Here we go. We're going to take the square root. Okay, square root of 9.6 times 0.226 times 0.895 cubed. And what do I get? I get a value equal to, and don't worry about that either, man, equal to 1.25. Okay, now let's make sure, let's double check. I'm going to try this again. In fact, I'm going to do it in reverse, right? I'm going to plug in all my values up here and see if I get the right Kc, okay? So I'm going to take 1.247, and I'm going to square that, all right? And then I'm going to divide that by 0.226, and I'm going to divide that by 0.895 cubed, and I get 9.6. There we go. So that works. All right. So you guys try this next one, and let me know if you have any questions. Bring me back when you're ready. Okay, here we go. First thing I want to do is write my Kc expression. This is going to be Hi squared, right? Once again, these are all gases, so I can use a Kc, and they'll be in there. But even though they're gases, I'm not putting in their pressures. Since I'm going after a Kc, I have to put in their concentrations, right? Moles per liter. Good. So here's my Hi squared, and remember it is an equilibrium concentration, divided by my concentration of I2 times my concentration of H2. Both of these are at equilibrium. Which one am I trying to find? Looks like I've given this, I've given that, I've given that, so I'm looking for my Hi. Okay, so we want to solve for Hi, multiply both sides by I2 and H2, so I'd get Kc times my concentration of I2 times my concentration of H2, and that is equal to Hi squared. And then that means what? I want to take the square root of both sides. And when I do that, I get that my Hi is equal to the square root of Kc times the concentration of I2 times the concentration of H2. Good. So let's put in some values. Square root times 54.8 times what is I2? 0.0752 times 0.138. 0.138. Good. Let's run the numbers. Square root of 54.8 times 0.0752 times 0.138 equals 0.754 molar. Now let's go check that by putting all of these values back up here, right? So I'm going to take 0.75411. I'm going to square that number, yoink. I'm going to divide it by my I2 0.0752, and I'm going to divide that by 0.138. And if I did this right, I should get 54.8, and I do 54.8, and I double checked, and everything's great. So that is my equilibrium value of Hi. All right, that's it, ladies and gentlemen. That's all you need to know for now. Let me know if you have any questions. Ciao.